All right, continuing our discussion on quantitative chemistry, we're going to delve into oxidation reductions just a little bit. By definition, an oxidation occurs when an atom or ion loses electrons. So the substance being oxidized loses the electron. The reduction occurs when an atom or ion gains an electron. Okay, and the substance being reduced is the one that gains the electron. So the idea is that the oxidized becomes more positive. The substance reduced becomes more negative. Now, sometimes chemistry, I share, what do you call them? Acronyms to help remember things. And there are two to remember for oxidation reduction. One is Leo says GER, and that is losing electrons is oxidation, gaining electrons is reduction. The other one is Red Cat. Nope. That will apply much later. Leo says GER. Oh, the other one that I use, actually, boy, it's been a little while, is oil rig. Oxidation is losing electrons, reduction is gaining. So either one, whatever helps you to remember that oxidation is losing and reduction is gaining electrons. Now, okay, so where would we actually see this? Well, typically it is in single replacement reactions. Not to say that it is only in single replacement, because it actually does occur in combustion reactions as well, but it is in easier seen perhaps in a oxidation reduction. So we have the single replacement of copper solid with silver nitrate, forming copper nitrate and silver metal. If I were to write the net ionic for this, it would be copper solid plus 2 silver ions in solution, it's a Q, goes to copper 2 ion in solution and 2 silver atoms solid. Okay, hopefully metal, think about it, what is the overall charge of metal? Well, it's 0. So it's really copper with a 0 charge on it. And over here it has plus 2. So to go from this side to here, copper had to lose 2 electrons. Kind of in the same vein, to go from a silver plus 1, 2 atoms, or 2 ions, going to make 2 atoms of the silver metal with a 0 charge, it had to gain 2 electrons. Okay? You cannot have oxidation without reduction. If something is going to be losing 2 electrons, there has to be something in the system to gain those 2 electrons. Otherwise, these reactions wouldn't happen. All right? Now, let's take a moment and look at these charges. So I have a 0 and a positive, plus 2, and a minus 2. Those are what is known as the oxidation states or the oxidation numbers of those elements and ions. So moving on to oxidation numbers. We're going to assign oxidation numbers to each element in a neutral compound or in a charged entity. And if they change from the reactant side to the product side, then we know we have a oxidation-reduction reaction. Those are commonly referred to as redox reactions. Right? So these oxidation numbers are really sometimes fictitious when they're in a neutral compound. Sometimes they are real, sometimes they're fictitious, but we assign them so that we can tell whether or not an oxidation-reduction reaction has occurred. How do we assign these numbers? Well, there's several rules to remember. You should write these down. and remember them because you will be asked to assign oxidation numbers. So elements in their elemental form have an oxidation number of 0. So metal in its neutral solid state would have an oxidation number of 0. So when you see a metal by itself, like we saw copper solid or silver solid, aluminum, any of those metals, it would have an oxidation number of 0. The oxidation number of a monatomic ion is the same as its charge, and you saw that in the example. Nonmetals tend to have negative oxidation numbers, although some can be positive. Oxygen typically has an oxidation number of -2. There are two ions of oxygen. One is the peroxide ion, in which it has an oxidation number of -1. Hold on for a sec. The peroxide ion is actually a 0 oxygen 2 with a -2 charge. Okay, so this -2 would be split between each of those oxygens, and each oxygen would be -1. Hydrogen is -1 when it is bonded to a metal. It is a +1 when bonded to a non-metal. Fluorine. Nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. Fluorine always has an oxidation number of -1. The other halogens have an oxidation number of -1 when they are negative, but they can have positive oxidation numbers, most notably when they are in oxyanions. So when you see that oxygen present, okay, if it's with a halogen like the that is the hypochlorite ion, the chlorine here would have a +1. This oxygen would be assumed to be -2. Then for the ion to be -1 overall, it means this chloride has to have a +1 oxidation number. And we'll look at several examples of assigning oxidation numbers. The sum of the oxidation numbers in a neutral compound is 0. And the sum of the oxidation numbers in a polyatomic ion is the charge on the ion. So let's look at a couple of examples. Let's see, let's look at nitrate ion. Let's look at calcium carbonate. Now let's look at those two. All right. Typically what I do is I say, okay, oxygen, oh, by the way, you may want to note that sulfur and nitrogen do kind of unpredictable things. Okay, so when you're looking at a compound and you have to decide the oxidation number of the nitrogen, typically you're going to leave that to last. Oxygen, typically a -2. I have 3 oxygens, so kind of this total is a -6. What we want to see is what does nitrogen have to be so that when I add its oxidation number to -6, I get the overall charge of the polyatomic, which is a -1. Hopefully you can see that this must be a +5. There's only one of them, so it must be a +5 oxidation number. If you look at calcium carbonate, okay, it is a neutral compound. Calcium is in the second group, so I know it has to be a +2. There's only one of them, so it's a +2. Oxygen's -2. There's 3 of them, so that has to be -6. These 3 oxidation numbers, I'm looking for carbons, have to add up to 0. In order for this to add up to 0, this must be A plus 4, so that means carbon's oxidation number must be A plus 4. Let's look at something like dinitrogen pentoxide. Again, oxygen, we're going to leave nitrogen to the end because sometimes that does weird things. Oxygen is -2, I have 5 of them, so this must be a -10. It's a neutral compound overall, so this nitrogen total, when I add it to a -10, has to equal 0. This obviously has to be +10, but there's 2 of them, so each nitrogen has an oxidation number of +5. Okay, and you'll see my work on keys that look like that. Okay. Take note that an oxidation number has the sign in front of it. So nitrogen's oxidation number would be a +5. Nitrogen's charge is a 5-. I'm sorry, 5+. Geez. Okay. Is it a subtle difference? Yes. Is it worth a point on the IB test? Yes. Do I think it's silly? Yes. Okay. There you go. Okay, we have looked at these. In displacement reactions, ions oxidize an element. The ions are then reduced. In this reaction, silver ions oxidize the copper metal. The reverse reaction does not occur. Well, why doesn't it occur? Well, it has to do with the activity of the metal, right, and the ease with which oxidation occurs. This is known as the activity series, and it basically lists the elements, metal elements, in order of reactivity. Oops. So, for instance, the most reactive metal, at least on this list, is lithium. So that means lithium as a metal will make any ion below it accept an electron to become the metal. Right? Keep in mind that typically these ions are more stable. Elements move towards a more stable state. So there is a lot of driving force for these metals to become their ions to become more stable. If it's paired with a more active metal, the more active metal is going to react to become more stable and kind of forcing the ions, if they're present, to accept those electrons to become the more unstable neutral metal. You are not required to remember or memorize an activity series. You do have to know how to apply it in predicting whether or not a reaction will occur. And that should end this. The next screencast will be on molarity, and titrations.